You can recognize printers from their painting. So there are really very different styles. And I feel in mathematics, the interest, the way of thinking of mathematicians are really very different.
Tell us something about your PhD thesis.
With my husband, we were in Poland in 56 September or so. I met Steinhaus, and Steinhaus mentioned a conjecture about the fractional part of an alpha sequences where alpha is an irrational. The distribution of this sequence in 0, 1. And I proved his conjecture.
And this is what is called the three-distance theorem.
This is what is called the three-distance theorem, and I became so much interested in it that I realized that this so-called three-distance theorem gives a possibility to give a new way how to start in the Diophantine approximation, how to define continued fractions, which is, of course, a basic tool in the Diophantine approximation. And I reproved a few theorems on that way, and I proved some new theorems, and this was really the subject of my thesis.
As you grew in your career in Hungary, you were always surrounded virtually entirely with men. How did this men's society receive you and react to you?
It was never an issue in my life in Hungary. It was never an issue in my own life at any other part of the world. But I must say that I had to learn that this is a serious problem when I came to the States, and maybe the first time in the middle of 60s. Of course, the 60s were the most important years from the point of view of feminism. And then I had to learn that this is an issue. It is a very delicate issue, and there are very different answers.
Vera, I just saw a paper in the Annals of Mathematics, and there is a paper in 2012 where you are one of the co-authors. You are beating all the stereotypes about mathematics being a game that is played by the young. Tell us something about the subject area of this 2012 paper.
I was able to take part in such a project and to work with the people by Christian Borks and Jennifer Chase and Kati Westergombi, and last but not least, Laci Lovász, who is the center. I really feel happy and lucky because of that.
So the subject is limits of graphs. Can you say just in a few words something about what kind of limits
Yes.
this is and where it is coming
Yes.
from?
The title of the book is Large Networks and Graph Limits, where the title indicates that the whole thing started, and of course now it is related to many things, but started with a study of large graphs. And now we all know that in graph theory, now this became, in some sense, a new, but really not quite new subject, but now it became more and more important. And partly because of the so-called real-life graphs, like the internet or the web, or large graphs in social sciences, in the brain and in the nerve system. And all these graphs, it's not only large, but one cannot know quite precisely the graph itself. partly because it is a growing one, and partly because you really don't know all the edges. And this indicates that the questions are necessarily different. What we have for finite graphs, for small graphs, we cannot ask most of the questions what is investigated or which was asked for finite graphs. First of all, it would be senseless to ask questions for properties, to investigate properties which depend only on a small number of edges. So you see the graphs, you see some global properties, and of course behind the global properties there are some local ones. But one has to ask at the very beginning quite different problems what for finite graphs. And now, which are these questions? And these are the questions we asked from really when we started to work on that problem. That when are two large graphs similar to each other? When do you say that these two graphs are close, if you have two large graphs, that these are close to each other? How the local and global properties are related. And again, last but not least, if you have a huge graph, how can you approximate it with small graphs or with simple graphs? So I mentioned maybe 4 questions. When we answer these questions, all these 4 or 5 problems we are looking for are very closely related. And then it turned out that it is related to many different parts of mathematics. Algebra, topology, analysis, and so on is involved in the whole study.
Can you say something about the connection to analysis?
Yes. At the very beginning, we defined the convergence of a graph sequence. Now, if you work with convergence, then the first question is, what is the limit object? Now, we met that problem when you have the rational numbers, and somehow you have a completion of the set of rational numbers, and then this gives one way. So here, as always, we would have that possibility, that just to consider the completion of the whole thing. But it wouldn't help to answer many, many questions. And the first thing what Lovász and Szegedy, Balázs-Szegedy did, they really found a very good object what to consider as a limit of a graph sequence. And the simplest way to formulate it, or the simplest object, is just a measurable function in 0, 1 square. One should consider more general spaces, so it is not necessary to stay with 0, 1 square, which turned out to be an extremely good model.
This limit concept, you mentioned that it has connections to many subjects, including physics. It also has some connection to the theory of computing. Can you say just 2 words about it?
Yes, that's true. Now, our idea is testing, mainly property testing. What we did, it was so-called parameter testing.
Another area that was among your interests, one of the main interests, about somehow the randomness-like features that you can observe in mathematics and outside mathematics.
Well, suppose that we know what randomness means for graphs. Yeah. So if flip a coin, if you consider just 0, 1 sequences and it is 0 or 1, and on that way you get a random sequence, And similarly, it started with Erdős and Rényi to consider random graphs. And quasi-randomness is a very surprising concept based on some very surprising facts. Namely, there are a lot of different properties of random graphs. I don't want to give a list because it is not quite a finite list. And then it turned out that quite a lot of different properties of quasi-random graphs are glued together. So if you have a graph sequence which has one of these properties, then you have all the other 5 or 6, which is a very surprising thing. That even when you have a graph sequence which is absolutely not a random one, but you know one of these properties, then you know all the other 5 or 6.
So let's say a specific example, for instance, the 4 cycles. So,
not the first, but simplest definition for quasi-random graphs is that if you have a graph sequence where the number of edges, say with probability half, is about the same as in the random graph with probability 1/2, and you know that the number of C4s, the number of 4 cycles, is the same, approximately, of course, so I will always give a precise formulation, as in the random graph, then these 2 properties imply a lot of other random-like property. So, for example, in a random graph, the edge distribution is uniform. If you take a not too small, if the edge density was 1/2, then if you take a not too small subset of the vertex set, then the edge density will be also 1/2 there. This is one important property of random graphs, but the same refers to the density of triangles, the density of Petersen graphs, or the density of any finite graph, that the distribution is quite uniform in the graph. And there are some other properties which are equivalent.
So who introduced this concept of quasi-random graphs?
Henry Thomason, who had some papers where he proved the equivalence of certain random-like properties. And then let me give the right order, Fenchung and Ron Graham and Richard Wilson, they gave a precise definition of quasi-random graphs, and they gave 5 or 6 equivalent properties. Equivalence in the sense that if you have a graph sequence, then it's trivial. If you have one of these, then you have all the other. And with Simonovic, we gave a, 7th one. And
yeah, but that was very important because you were linking that to the Semeredi
to
partition.
the Semeredi regularity partition, yes. And now I can speak about 7 or 8, I don't know, equivalent properties of graphs. And all random graphs have these properties, but this is, of course, a much larger class, because there are a lot of properties of random graphs, but quasi-random graphs do not have.
You can't recognize that a graph is random, but you can recognize if the number of 4 cycles is about right.
You cannot check all the properties of a random graph, and of course quasi-random graphs can be, from certain point of view, quite deterministic.
So maybe at this point you could outline what the Semeredi partition is?
So Semeredi partition means that if you have a large graph, then you can partition the vertex set into a certain number of classes, where the number of classes is not too large, it is really bounded by something. And if you consider the edges between two classes, this is very much random-like. So which means, which is a very surprising fact, that an arbitrary graph which is large enough and which is dense, so all what I am saying refers to dense graphs, which means that these have constant times n square edges. You have finitely many pieces where all the edges behave like random graphs. So means that one can build up an arbitrary graph from not too many random-like graphs.
And can you now indicate somehow how this connects up to the limit concept?
What does it mean that a graph sequence is convergent? And it can be formulated in different form. One is that the Semeredi regularity partition converges. Another is that the density of small subgraphs converges. And the other is that the edge distribution converges in certain sense. And of course, not all these graphs are random or random-like. So for a general class of graph sequences, this is true. And what is a surprising fact, that these three properties, edge distribution, Semeredi partition, and small subgraph frequency, are equivalent properties, so with in proper quantitative form, equivalent properties of quasi-random graphs. These properties are really glued to each other in a much more general world than just quasi-random graphs.
What age did mathematics catch your attention?
About in the age of 14 or something like that. I survived Holocaust. And when after this story stopped, so at the end of the Second World War, and when we went back to school, this was in 45 March, then we had a new mathematics teacher, because the previous one did not survive the war. Was not a survivor of the Holocaust. And so I met Tibor Gallai, who was my teacher in high school, so for 4 years. And I think he is really responsible for that. It was a remarkable high school. It was a Jewish high school. We really had extremely good teachers.
Was it just girls or was it co-ed?
No, it was a twin school. There were doors between the two schools, but it was not a co-educated school, what you mean.
So your class was girls only?
Yes. About the third of my schoolmates, girls, went to study to university or to college in mathematics or in physics. And this is definitely due to Gallai. So I can't say that this was typical, or I can't say that it is typical now. in a girls' school, say, but not even in any school.
And you are not the only one who became a mathematician.
Yes, of course, I am not the only one. So I have Edi Gyarmati, with whom we started to go together to even elementary school. So when I was 6, we were 6 years old, and then we worked at the same, we had jobs at the same university, at the Eötvös University, and actually we shared the same room for many, many years. Yes.
So tell us a little bit about Tibor Galvai, the legendary teacher.
He was already a well-known mathematician at the time when he came to teach in the school. So he was an excellent mathematician, he was an excellent teacher, and I would say that above all these, he was, the word excellent is not good, but an extraordinary human being. He felt that we should learn or meet somebody who really can give something more. So this is how I met Alfred Rényi.
So you were 16 at the time and Rényi was 20-something?
About 10, 11 years older. Mm-hmm. And then, because after a year or so, he went to the former Soviet Union to be a aspirant, a PhD student of LINIC. So he forwarded us into the hands and brain of Rózsa Péter.
But even in this shorter period before Rényi went on PhD study to Leningrad, he already engaged you in mathematical discussions.
We started to meet Rényi quite regularly, and he gave problems, and the next week we came up with a solution, or we came up with a problem that we do not find a solution. And beautiful problems, but I must say that already Gallai gave beautiful problems in the class.
People often ask, what is the key to the success of mathematics in Hungary? And I would say that you just illustrated this kind of very early mentoring, yes. that is very few places can say that this is not entirely singular. Your case is clearly singular in many ways, but there are many others who would also describe that they were already mentored by major mathematicians.
Yes, exactly.
At an early age.
Exactly. So Rényi was not a high school teacher. Rózsa Péter was for a while, but Rényi was absolutely not. He was a quite well-known mathematician at that time, and he was willing to meet these small girls.
So what did you learn from Rózsa Péter?
She was a logicist, and I think she became really well-known because of her book on recursive functions, which is even now quite often quoted, and which became important also in computer science, which was not clear at the time at all when she wrote that book.
She also wrote a very popular book.
That is true. The title was Playing with the Infinity. And actually the book was translated to at least 15 languages or so. And the book has always a new edition, at least in Hungary. And this was really a very, very remarkable and unique presentation of mathematics for everybody. Mm-hmm. She was the one who was a teacher in high school, Then she became a teacher at the Pedagogical College, and then she became a professor at the university, where we were at the same chair. So I had the pleasure really, and I was lucky that I met her quite often.
What were the early subjects that she, I don't know, discussed with you?
It is very interesting because when Galai suggested to Rényi that it would be good if he would find time to meet us, then of course he told okay, and this is how things started. But when Galai, or maybe also Rényi, suggested to Rózsa Péter that she should follow what he did, Rényi, then we had to go there. So she asked some logical questions, you know what one can ask, which is formally, it is not mathematics.
How did you fare on the logic puzzles?
I did like it very much.
Okay. Now, Rózsa Péter's character was very different from the other people you mentioned. Can you say something about her as a person?
Teaching was really her life. She was, of course, extremely good in mathematics, and for her, teaching was the most important thing in life. So one interesting thing is that she prepared for each lecture in her course so that she learned it really, word by word, literally. She really wanted to give the very best lecture, and which means that each sentence has to be the most correct one, and the structure of the lecture had to be the most correct one. And she asked the students quite often, and when she got the wrong answer, then she started to quarrel and to shoot. And this happened not only during the lecture, but during the examinations she gave. Mm-hmm. And this had the consequence that after a while, she realized that she cannot resist to be angry and to shout with the students. So she gave up examinations, to have examinations. This is about the end of her story. With Rényi, I had quite strong contact. I was a sort of assistant of him, so even in the third year I gave seminars, and then later on we have some joint papers, and I had really that opportunity to work with him. Rényi was an extraordinary human being. He was able to be active in 5 different things at the same time. It is really remarkable. He died before he became 50. He wrote books which are quite unusual about the philosophy of mathematics, about philosophical questions of information theory. And maybe it is not quite clear for everybody who reads his books. It was also about politics.
So, I mean, this was the era of Stalinism and then the softer communism that followed.
Yeah, he had very strong views. It was mostly the politics of science, politics of doing science, politics of leading science, politics of the universities, and so on.
So one of his great accomplishments was the creation of the institute that now bears his name.
Rényi was, in some sense, the second director of the institute. Before the present institute was founded, there was an institute called Institute for Applied Mathematics, and this was attached to the Technical University, and I don't know how much to the academy, and the director of that was Egerváry, Jenő Egerváry. And then the whole became a much more organized and a larger institute, and an institute which was and is attached to the academy. This is what is called now the Rényi Institute of the Academy, of the Hungarian Academy of Sciences. And really, he was the first director and the director until the end of his life.
When did you first meet Paul Erdős?
Erdős came back the first time after the war in 1948. One has to know that his mother lived in Hungary during the war, survived wartime and Holocaust, and lived alone. Next to the school where Galai was a teacher and I was a student. And Galai visited, of course, very often Erdős' mother. So because Erdős was far away, in some sense he tries to substitute him. And time to time he took not only me but some other students to introduce to Erdős' mother and to spend there some time, because Erdős' mother was a math teacher. Since I was interested in mathematics, so it was maybe not so surprising that Galai introduced me to Erdős.
So you were one of the epsilons of the time for Erdős when Stalinism was introduced to Hungary after World War II. Then the borders were sealed, and Erdős himself also was advised that if he comes back to Budapest, he may not be able to leave. So that's why there came this other 7-year period that he did not come back. And eventually he got an assurance that if he comes back, he would be able to leave, and then he came back. Right. So can you tell us something about Erdős's legal status vis-a-vis Hungary, so how he could travel back and forth?
He really could travel back and forth, which was not quite trivial in that period, in late 50s and early 60s. And he was able to do that because he had a very special passport.
So in 1950, as a sign of the politics of the time, there was a very special Congress of mathematicians arranged in Hungary as sort of a counterpart to the International Congress of Mathematics, to which Hungarian mathematicians would not get the exit visa from the communist government.
Yes.
And so can you say something about who participated in this counter-congress in 1950?
I think all the Eastern European countries were represented, and all the very best Russian mathematicians, or
including
most of them, including Vinogradov. And I think Linik too.
Mm-hmm. Yes. And you were 20 at the time,
20.
And you were a participant, and you were a speaker at this Congress.
Yes, this was my very first lecture or talk, small, 20-minute long, at a Congress.
You also had a ceremonial job. at that meeting?
Well, yes. Yes, because I was the youngest participant of the Congress. My honorable job was to greet the delegation of the Soviet Union, including Vinogradov.
Mm-hmm.
And of course, this was also translated, but it was translated to Russian.
Uh-huh.
And I did it.
So,
Yes.
Can you tell us something about what your lecture was about?
At that time, I was very much interested in complex function theory, and Rényi was also very much interested in complex function theory, not only interested, but he was active on that field. And he formulated some problem, which was actually a geometrical problem, but related to so-called Schlicht functions. And I solved the problem, and this was the subject of the talk.
Mm-hmm. Tell us something about your PhD thesis.
My PhD thesis was on Diophantine approximation.
Okay. And this is one of the major loves of your mathematical life.
With my husband, we were in Poland in 56 September or so. The year is important. And I met Steinhaus, and Steinhaus mentioned a conjecture about the fractional part of an alpha sequences where alpha is an irrational. The distribution of this sequence in 0, 1. And I proved his conjecture while being in Poland.
And this is what is called the three-distance theorem.
This is what is called the three-distance theorem, and I became so much interested in it that I realized that this so-called three-distance theorem gives a possibility to give, in some sense, a new way how to start in the Diophantine approximation, how to define continued fractions, which is, of course, a basic tool in the Diophantine approximation. And I reproved a few theorems on that way, and I proved some new theorems, and this was really the subject of my thesis.
One of the results, maybe in the thesis, you discovered a new lovely extremal property of the golden ratio. Can you say something about that?
Yes, because one important property of this N alpha sequence is that it is uniformly distributed in 0, 1. By the way, the first time I heard from Rényi about this fractional part N alpha sequences, where he gave as a problem that this sequence is everywhere uniform, everywhere dense.
And Rényi asked you this question still while you were in high school.
Yes, yes. He did not ask the question to prove the question that how could I prove that it is uniformly distribution. I think it was just everywhere dense, if I want to be honest.
Okay.
But yes, and with a French colleague of mine, with Dupin, we proved that actually this N alpha sequence belonging to the golden ratio is the best one in the sense that uniformly distributed sequence cannot be very, very good. It has a limit how well distributed it can be. It is a theorem of Wolfgang Schmidt, and we proved that that sequence is the best one. From the point of view of uniform distribution,
so the fractional parts of the multiples of the golden ratio are somehow the most uniformly, uniformly distributed as it gets.
As it can be.
Mm-hmm. This theorem had a huge career even outside number theory. I first saw it actually mentioned in Donald Knuth's book, The Art of Programming.
Yes, but maybe the relation of N-alpha sequences to other fields is more present now because it is very much related to dynamical systems and to ergodic theory. So this means that what one can see some special properties on the fractional part N-alpha sequences, quite a lot of properties hold for the orbits of a point in an ergodic transformation. So this is one thing, and really in dynamical systems itself, the Diophantine approximation, the fractional part N-alpha sequence, plays a very, very important role. A very recent result, which is due to Alan Lindenstrauss, who received the Fields Prize 2 years ago. And one of the reasons was that he had some very important results in a conjecture of Littlewood about some properties of simultaneous Diophantine approximation. The conjecture says that if you consider simultaneous approximation, which means that, for example, you have two irrationals, then the whole Diophantine approximation problem becomes much, much more difficult. And one can't say that anybody can see the whole picture in simultaneous approximation. But the Littlewood conjecture formulates in a precise form that if you take a pair of irrational numbers, this pair cannot behave too badly from that point of view. And at present the world is, I think, quite far from having the proof, but Lindenstrauss proved that it is, if there are bad pairs at all, then it must be a very small set. By the way, that problem you can find on Gauer's blog, if everybody knows about it, and he formulates again and writes about the present situation of the Littlewood conjecture among the problems he used to mention on this polymath project.
So let's turn back the clock a little bit to your PhD. You wrote this in the fall of 1956. This was a very turbulent time in Hungary. That was the time of the Hungarian Revolution, uprising against Soviet domination, and at the same time you had a 3-year-old child. How were you able to write your dissertation under such circumstances?
Just because the life was not quite normal, and there was fights on the street and everything. Of course, the school stopped and university teaching stopped, so I had much more time. Of course, I never left home, and for a while we were in the basement, and there I had more time than ever before, and then I had time to write and to work on that problem.
So that's one instance of being able to do creative work under rather depressing circumstances, like when there is street fighting outside and you are afraid that your house can get a hit.
Yes, but I don't think that this is such a very important example for that. Much better example is what my husband Paul Turan did while he was in labor camp.
We are talking about forced labor companies in 1944.
Yes, and this was
Nazi.
in between 38 and 44. Several times he was in labor camp.
People of all walks of life, including academics, including well-known scientists, were sent to do manual physical labor. Paul Turan was one of those mentors, my mentors, who actually did mention this to students on various occasions on graduation, and he mentioned stories about how he was able to do great mathematics under the worst of circumstances. So one of these cases involved him having to repair, electrical wires on the top of a telephone pole. And Vera, maybe you can say something about what theorem was born.
This was a Turan extremal graph theorem, which says that if you do not have a complete graph of a certain size, then you cannot have too many edges. And this is what he determined, the maximal number of edges what a graph can have.
Paul Turan's usual comment to this was that in contrast to the analytic number theory, for which he would always need paper, graph theory he could do in his head, and that gave him freedom.
And in some sense, it saved his life, because he was able to work in mathematics in that circumstances. So working in a brick factory, he realized what is a mathematical problem, what they have when they had to carry bricks.
I heard this from Paul Turan himself. He talked about this too at events, at graduation events, and it was one of his favorite examples of how good mathematics can come out of abominable circumstances. So he had to push this cart, and wherever the rails would meet, the cart would somehow, just some bricks would fall off the carts, and so it occurred to him how one could draw a graph in the plane with minimal number of intersections. So this became an important problem in graph theory.
Not only in graph theory, but in electric engineering, I think. So the problem came from real world, and it became important in designing
printed circuits.
Yes. And the other thing, which has even a longer story, that he find his so-called extremal graph theorem in labor camp. Graph theory was not at all his subject. His subject was analytic number theory. And why he started to think on graph problems, was because, as we know, in analytic number theory, you really need paper and pencil. It needs a lot of writings, it is full with formulas, but not in graph theory. So in graph theory, you can think on the problems when you are forced to be on the top of a telephone pole, and this is what he did. Maybe one of the most developed class of problems or theory in graph theory is the so-called extremal theory. And extremal theory became important not only in graph theory, but in set theory, in a lot of different structures.
You initiated a connection between extremal graph theory and Ramsey theory, so the so-called Ramsey-Turan type questions. Can you say something about this area?
We had a problem with Erdős. We formulated for hypergraphs a very innocently looking problem. And it turned out that it became important also in this additive number theory, in the Semeredi type results. So For example, now in Minnesota, where there was a conference on Semeridi, about Semeridi and Abel Prize, then out of the 10 lectures, maybe including mine, it was mentioned 3 times, because it was thought the problem was solved by Ruja and Semeridi, and then it turned out, and it is again a very surprising part of the history of mathematics, that this extremal hypergraph problem turned out to be strongly related to additive number theory, more exactly to arithmetic progression and things like that.
Now, this is the so-called 3-6 problem. Could you state what that problem was?
Yeah, it is very simple. It is a special case of a general problem. If you have a triple system, which means that you have points in the space and points, and you take a few from the triples. And you know that if you take any 6 points, you will have at most 2 triangles, which is spanned by this, which belongs to these 6 points. And which means that less than or equals 3, less than 3. And so it became the so-called 6-3 problem. And therefore
But the question is, what is the maximum number of triples you can have? So it's the density of the triples.
Yes, what is the maximum number of triples? And Ruja Semeridi proved it. And it turned out already in their paper that it is very strongly related to arithmetic progression questions. And if you mention that I should mention it explicitly, that I must say that the next value, so taking instead of 6, 7,
so instead of 3, 6, taking 4, 7, yeah.
And taking 7, 4, the similar problem, then it is still unsolved.
One of the most interesting variations on the classical themes of extremal graph theory that I encountered a few decades ago was also a problem that you had introduced. It is this structured intersections questions. One of the main questions that you proposed in this area was somehow solved exactly on time, that the authors were able to present it to you on your 80th birthday conference.
You have a class of graphs, say on the same number of points, and if you take any 2 graphs in this family, then you know that there is a triangle which is contained in both graphs. So we would say that any 2 graphs intersect, the intersection contains a triangle. How many graphs you can have in the family? And we asked that, I don't know, more than 30 years ago. And several, I don't mention the names really, several people tried to solve the problems. And about 2 years ago, Ehud Friedgut and Alice and means 2 of his students, they proved the problem, they proved the conjecture. The proof is very involved, or quite involved, uses discrete Fourier analysis and spectral theory. And they managed to finish, to write on the proof, really, when there was a conference you mentioned, and I must say that this was the most valuable birthday gift.
would you say something about how you met your husband, Paul Turan?
He was at Eötvös University, a professor. I was a student there, and after I finished university, we married. We have 2 children.
And you have some joint mathematical papers.
We have some joint mathematical papers, not too many. Maybe 5 or 6, and all but one is on graph theory. And the question is why? Because I would formulate, I think like in many fields or in art, so painters, you can recognize painters from their painting. So there are really very different styles. And I feel in mathematics there are also the interest, the way of thinking of mathematicians are really very different and very characteristic for certain mathematicians. And his main subject, and I would say that he was an analyst in some sense, and his main topic was analytic number theory, but really an analyst. And I am not. So I am more on the discrete part of mathematics.
Can you say something about the subject?
One subject is related to the theorem, extremal theorem of Paul. And we wrote with Erdős and Meyer, so 4 of us, a sequence of papers on the application of extremal graph theory, applications in complex functions theory, in measure theory, in potential theory, so really on very different parts of extremal graph theory. There was a mathematician, and this was in the early 70s, who formulated this sentence, and I am sure that you will not agree, that graph theory is just the slum of topology. And this actually shows that graph theory was not always so much accepted as it is now. But my husband was very, very much annoyed by this. Even he did not work on graph theory. He had really 2 papers or so. And he wanted to show that this is not the case. Of course, now everybody agrees that graph theory is not an isolated subject, but related to everything, or almost everything. But the situation with graph theory was much more difficult in these years. Mm-hmm. And this is how we started to work on it.
Yeah. People sometimes ask, you were a beginner in your career, essentially, and Paul was already a well-known mathematician. Was that not somehow intimidating?
Among mathematicians, the hierarchy in some sense doesn't exist, at least in Hungary. I had that feeling. I don't know what was your experience. So a very strong hierarchy exists among lawyers and among doctors and maybe in some other fields, but definitely not in mathematics. As you came up with the subject, I met Rényi when he was already a well-known mathematician. Actually, Gallai was already an internationally known mathematician. Rózsa Péter was. And this was not a distance in Hungary between students. And is it your opinion too?
So people say that Paul Erdős was such a gentle person that he would treat every young mathematician as an equal. But perhaps this is not so entirely unique for Paul Erdős. You are now hinting at a tradition that you were also immediately accepted by this community.
But not only me, but
yeah. Yes,
many other young people.
Would you like to add maybe some strokes of paint to the about the character of your husband, Paul?
He had a very difficult life until he came back from Princeton to Hungary in 1948. Well, he was in Princeton just after the war for a short time.
So he survived the entire period of persecutions in Budapest.
He survived Holocaust, but his two brothers and his sister, so they were four, did not survive. And so life was not so easy for him. He had no job at all. My older son, Gyuri, when he was maybe 6 or 7 years old, once asked him how often he thinks about his brothers and sister. And he had a very short answer: every day. So maybe this gives some, yeah. Next.
Yeah. But somehow, I don't know, the legend has it also that he also enjoyed life very differently from Paul Erdős.
He enjoyed life, I agree. But Erdős also enjoyed life, not in everything what Paul, but maybe he enjoyed music very much, like Paul. Music was extremely important for him. Sport was important for him, maybe not so much important like for Paul. And for Paul, history, so for my husband, history was extremely important. So he was always very much interested, and literature was very important for him. It is not a correct and fair picture about Erdős, that he enjoyed only doing mathematics. This is absolutely not a fair picture about him. His empathy was really extraordinary, and he liked social life in some sense, but a bit differently.
So one of the perhaps most fascinating archives in mathematics is in your possession, and that is the correspondence between Paul Erdős and Paul Turán between 1938 and 1942, when because of the war, correspondence between Hungary and the West stopped. Can you say something about this correspondence?
We have not only the correspondence from these 4 years, but for a whole period when they were far from each other. But I chose these 4 years to write something in the Erdős 99 volume. I had the feeling that this whole wartime is not so much known by everybody. Yes, and this correspondence is extremely interesting. By the way, it contains a proof what I said before, that Erdős was very much interested in sports, because in these letters they exchanged ideas not only about mathematics, not only results what one of them heard in that country or in the other one, but also about the everyday life in Hungary. So Erdős was interested who won the tennis team on the day before Paul wrote the letters, because he played tennis, for example. So this proves different things. And was interested what his other friends are doing, in which situation they are. They discussed in the letters that they were students of Fejér, Leopold Fejér, and he had many students in some sense, because almost everybody finished his PhD with Fejér, but his behavior with the students was a bit different. What maybe they expected, and Erdős was interested that what is doing Fejér now, what he should do to improve the connection, and so on. So you find all parts of life and the opinion and the interest in these letters.
Talking about Turan stories, maybe I could relate another one. In the late 1930s, he wrote a paper with Paul Erdős. Paul Turan and Paul Erdős wrote a paper in number theory that was related to the work of a Russian mathematician, and they published it in a Soviet mathematical journal. And now in the late days, in the waning days of Nazism in Budapest, where the Nazi gangs would roam the streets of Budapest and round up Jews and then collect them in a cellar and then take them at night to murder them at the river Danube and wherever they could. In those days, Turan was also fell into this kind of into the hands of these roaming Nazis, but he somehow managed to escape out of the cellar. A few days later, the Russians took Budapest, and the Russian soldiers asked identification from the man that they met in the street. Whoever did not have identification was suspect of having been a soldier, was sent to labor in Russia for years. And Paul Turan was asked about his ID, but his ID was collected by the Nazis a few days earlier, so he did not have that. But he did have a preprint of the paper that he had published with Paul Erdős in a Soviet journal in the era when there was greatest hostility between Hungary and the Soviet Union. And so the officer accepted that, not only as an ID, he would let him go. And then in one of the first letters, you must have encountered this letter when you looked at the correspondence between Paul Erdős. Paul Turan reported to Paul Erdős that was a remarkable application, an unexpected application of number theory. Fejér was probably one of the major early influences on your mathematics. Can you tell me something about your interaction with Fejér?
Yes, first of all, I attended the lectures of Fejér, which was very special because I attended also these lectures, and these are the two famous Hungarian mathematicians from that time, and they had completely different style in giving lectures, in personal contact, and so on. And Fejér was somebody who gave just a small part what he should give in complex function theory. This is what I learned from him. But his main idea was to show the beauty of mathematics. He was able to speak on a small theorem for an hour and to point out all the different features of the beauty of that theorem.
Mm-hmm. You also had some personal
Well, I was, then when I finished university, I was his PhD student. But as you see from what I said before, finally my subject, the subject of my PhD thesis was not complex function theory. But I also mentioned something which shows that I was very much interested in complex function theory at that time.
Yes. And how frequently would you meet with Feyerabend?
Weekly. I went to his home, the apartment where he lived, and it was not a structured teaching, nothing planned in advance. Mm-hmm. It was always a surprise for me. If somebody wanted to understand the beauty of mathematics, then Feyer was a right person.
So some of your major influences were analysts. I mean, Paul Turan was an analyst. I mean, Paul Erdős really grew up as an analyst. Then here was Ries, Feyer, and you said, okay, but you were not an analyst.
No, however, absolutely not.
However, throughout your career, you taught innumerable classes in analysis.
And I really enjoyed very much, and maybe as a university
teaching analysis, yes.
Teaching analysis, and maybe I was at the university for 35 years, and I gave lectures for 35 years or more, and this was my main subject on what I gave lectures. The other one, graph theory.
But you also wrote a very successful textbook.
Yes.
About analysis, and now there is a new incarnation of that.
Yeah, actually with Miklós Lackovics, who used to give the very same lectures for years, and fortunately he has the very same opinion how to give a lecture, because this can be very, very different. And the very same taste.
Your lecture notes had maybe 30 editions or something. It's a very large number of editions. So it's a generation after generation in Budapest learned analysis from your text. And then now you have this book with Lackovics that is being translated to English. Is that correct?
Yes, it is just under translation
by Springer. And it will be published by Springer.
By Springer.
Vera, you mentioned that this subject of the fractional parts of the N-alpha sequence are related to dynamical systems, to ergodic theory. Could you say a few words about the connections?
I was always excited when I realized that between two fields which seem to be completely far from each other and for completely different methods and everything, it turns out that there is a strong interaction. And this is what I can say about N-alpha sequences and dynamical systems and ergodic theory, and even more, or to prove. So when I started to work on graph theory and discrete mathematics, I would say also combinatorial number theory, then I did much less. I will not say that I left, but I did much less on Diophantine approximation. A few times I turned back, and this was always, I think, by an occasion when somebody asked me or a problem on Diophantine approximation or on N-alpha sequences, where the problem came from dynamical systems and ergodic theory. The first time was when Dorothy Maharam and Arthur Stone asked a problem on, in some sense, a characterization of alpha by a sequence of integers, not by the continued fractions, but by a sequence of integers for which you get a very good approximation for alpha. And the characterization of these three. On that problem, we did work with András Bíró and Deshoulier, and so I have maybe 1 or 2 papers. This was maybe 15 years ago or so. Another occasion was when Sinai, also as we know in dynamical systems and ergodic theory, asked a problem, simultaneous Diophantine approximation. What he asked, it is a question about a phenomenon which could be similar what we have for N-alpha sequences. And we answered this question with Szekes. And the third time I met or realized this strong connection of Diophantine approximation and physics is the story of quasicrystals. It is really a very admirable and wonderful story in the history of physics and in the history of mathematics. So Shechtman, who is a physicist in Haifa, in 1982, he is a material physicist, and he investigated the atomic structure of different materials. And as we all learned in school, I think at least I learned it, but everybody learned in school, that the atomic structure of you have 2 different forms, either crystalline, so a very periodic one, or amorph, which means a very random-like one.
Amorphous, yes.
And he did find something which is between the 2. And these are called now quasicrystals. And he realized that phenomenon when he investigated the atomic structure of aluminum and magnesium.
Alloy.
The alloy of magnesium and aluminum. And using electronic microscope, where one gets a so-called diffraction pattern, which shows somehow the atomic structure, he got some extremely interesting results. This showed something which could indicate that it is a crystal, because it showed a lot of periodicity or similar properties. But at the same time, it showed some 5-fold symmetry. And since we know that in the space there is no
crystals cannot have 5-fold
crystals can't have, so which is a mathematical fact actually. It was neither a crystal nor an amorph structure. And it showed an extremely interesting similarity with the Penrose tiling, where, as we know, Penrose tiling is a tiling of the plane which is not periodic, but periodic from almost periodic, or now we say it is quasi-periodic, which means that it has a lot of different properties what periodic system has. And what is behind in that similarity? But it was quite clear that there must be. And now how is it related to fractional part and alpha sequences? Now I would say shortly that a fractional part N-alpha sequence is nothing else but a one-dimensional Penrose tiling. Namely, De Bruijn proved that how you can generate a Penrose tiling. You take the 5-dimensional space and you take a proper strip and lattice points between those 2 points and project it on a proper way to a plane, and then you get exactly one of the Penrose tilings depending how you choose the planes. Which means this shows already that from the lattice, which is a periodic one, how you get this quasi-periodic one. And now how to get the fractional part N-alpha sequence. You do exactly the same. You take the 2-dimensional lattice, you take a proper strip, you project it to a line or to another line, and you get either the integer part or the fractional part of an N-alpha sequence. So you get, and this shows in some sense that why we can say that a fractional part N-alpha sequence is a quasi-periodic one. Not only because the three-distance theorem, because the three-distance theorem is one thing, but actually if one has the three-distance theorem, what now many people proved it, but I proved it and used it, it is not just that it has the three-distance property, but it has a lot of periodic-like property.
Paul Erdős has been legendary as a collaborator, and you are one of his foremost collaborators. Somebody compiled a list of collaborations, and you are listed as number 5 among his lifetime collaborators. Now, you first met Paul Erdős in '48, but you did not immediately start working together. When was it that you actually became a collaborator of Paul Erdős?
I really can't point out which was our first paper and when we sat down at the first time to work, but that is really true that whenever he came to Hungary, we tried to work on something, and whenever we met abroad, we worked on something.
Mm-hmm. So how often would Erdős visit Hungary after '56?
First, I say how often he visited before '38, because he left '34 and went to Cambridge, and then 3 times a year he came back very regularly. After '56, I would say yearly, and maybe for longer time, because his mother lived in Hungary, but later on he forced his mother, or I don't know how to formulate it, to travel with him.
There was also this resort in the Matra.
Yes, yes. So he did like to, when he came, then he spent a month or even more. And actually, what most of the people maybe really don't know, that for many, many years, actually until the end of his life, he had a sort of job at the Rényi Institute. The sort of means that he had a job, he was paid for as many months as he spent in Hungary, but this was his only permanent place, really.
And he also had an apartment in Budapest.
Yes, but after his mother died and his mother lived in that apartment, he never lived in that apartment really, then he refused to enter the apartment. Yes, so he was extremely sensitive, really.
But he would lend that apartment to friends and colleagues,
yes,
to live there, so that was put to good use in the apartment.
Yes.
So can you say something about the subject of your joint papers with Paul Erdős?
I mentioned one, which was on extremal problems of hypergraphs, And in that paper, writing that paper, this conjecture in a more general form. We formulated that conjecture.
You mean the 3-6 conjecture?
The 3-6, but of course in a general form. And then it's really, as you mentioned, Ramsey-Turan, which is why it is called, because there is a famous Ramsey theorem and now a Ramsey theory. In every disorder you find some order. If you take a graph and you take the complement of this graph, so two arbitrary graphs, then either the graph or the complement must contain a very ordered structure, substructure. First it was formulated for complete graphs, so it must contain a complete subgraph which has the size depending on the number of vertices and large enough. And then it came up the question, in some sense, a combination of the Turan-Extremal theorem and the Ramsey theorem, that the combination of that leads to interesting questions, and some of the questions are still open. And we started to work on this with Erdős, and then András Hajnal joined to this club, and then Szemerédi joined, and then Simonovic joined. So the last paper on that subject is a 5-tuple paper.
The Turan problem asks how big a graph can you have without a clique of a given size. Ramsey prohibits large cliques as well as large independent sets. And now you combined these two. So the extremal kind of graphs that come out of Turan's theorem, they are prohibited by these extra conditions, and that leads to a new world.
Yes, and would say add that the so-called extremal graph, which has a maximal number of edges without containing a complete graph of a certain size, has a very special structure. And in this very special structure, we have very large empty graphs, which means very large parts where we do not have an edge. And but if you try to see what happens when you try to move from this very special one. So for example, when you suppose that you don't have a large subset without any edge, then this is actually the Ramsey-Turan type problem to answer the question how many edges you can have in such a graph. And this is already a question. Nowadays, I think it is good to mention the name of Szemerédi, who got the Abel Prize not so long ago, that Szemerédi, so-called Szemerédi regularity lemma, so the main lemma what he used, or almost that one in his famous RKN problem, arithmetic progression proof, used also here, is used also here.
This is maybe one of the good examples that you always like to look behind the phenomena and somehow try to find some core reasons and explanations.
To give a proof where you don't see the real reason why the theorem is true, it is not enough. So, in some sense, so if I mention the four-color conjecture, if I may, then this is a good example that there are some people who still feel that you do not see the core of the proof. And this can happen in many cases, and when you are looking for the real meaning of the proof, then you often find such problems, I think.
While you contributed to mathematics with proving a lot of theorems, maybe some of the most important contributions you made were actually in questions. We already talked about the question that was recently solved about structured intersection theorems. Lovász, in the introduction to the book on graph limits, points out that when you arrived at Microsoft Research, where this small group that developed really the entire theory, was that you immediately proposed some questions that some people are still working on. Would you like to mention some of the questions that you injected into this project?
Yes, there is a concept of quasi-random graphs. It's a very well-defined class of graphs which share a lot of equivalent properties with random graphs. So they are not random graphs, this class is much larger, but there are quite a lot of important properties which are the same as for random graphs. And this whole theory started with some work of Thomason, and then Fenchung and Ron Graham and Richard Wilson wrote a sequence of papers which can be considered as the foundation of quasi-random graphs. And where in the very first paper they really formulated 6 or 7 equivalent properties, and then with Miki Simonovic we added a 7th or 8th one, which was that quasi-random graphs can also be characterized by the famous Szemerédi regularity partition, by the partition. And if you consider really that it has very special densities, and if you really consider the main meaning of the Szemerédi regularity lemma, then this means that he proves the possibility of the approximation of an arbitrary graph by, in some sense, graphs which are composed by quasi-random graphs. So I am not saying that can be approximated by quasi-random graphs, but which can be approximated by the composition of not too many quasi-random graphs. And if this is so in some sense, this is a generalized quasi-random graph. The object, what is the object in the Szemerédi regularity lemma? And I think it was a quite natural question that how to generalize some of the results which we know for random graphs, quasi-random graphs, for these general quasi-random graphs, because this would give even more light on the whole Szemerédi business. Because the Szemerédi regularity lemma itself is on large graphs. The quasi-random class is also about large graphs because it is really formulated for a sequence of graphs. And because the world was full with, the mathematical world was full with investigation of large graphs, what I mentioned before, so it was quite natural to have the feeling that maybe Szemerédi regularity will be one of the approaches. There are 3 basic properties of quasi-random graphs, namely that small subgraph frequencies, one thing, edge distribution, the second thing, and Szemerédi partition, the third thing, are very closely related. The behavior of any of these 3 leads to the same thing that you can recognize quasi-random graphs from the behavior of these things. These are very special for quasi-random graphs. It is, just to say one word, a random graph is very uniform, and the quasi-random graph, for example, from the point of view of edge distribution, is also very uniform. and so on. And what we proved in a few papers, so this was far not the end of the story, but in the first few papers, that these three properties, what I mentioned, are very strongly related for an arbitrary graph. So if you know any of these three, that for the two graphs, from the point of view of this property, the two graphs are similar. So say, for example, from the point of view of edge distribution, which of course not necessarily uniform, that they are very similar from the point of view of the semi-ready partition or the frequency of small graphs. And if you remember what I mentioned as the very beginning, that there are at least 4 problems what one would like to answer when you have to work with large graphs, that when we can say that two large graphs close to each other, when we can say that they are similar, when we can say that local and global properties are related, and when we can say that the graphs can be these huge graphs can be approximated by small or by simple graphs. This is just a theorem, so now the equivalence of these three things which answer that question in some sense. Because this shows that the 4 questions we can ask at the very beginning somehow go together. And we wrote these papers together with Christian Borgs, Jennifer Chase, and now I say Laci, so in the right order, and Kati Westergombi and me. But really, then in the whole thing, Laci is in the center, because many things happened since that time, and why I am very lucky that I was able to take part. So what you mentioned, that I like to find the core and like to find interaction between different subjects. So when you define the limit, on that way we define the convergence of a graph sequence, then the first question is that what is the limit object? And Lovász-Szegedy proved that you can consider different things as a limit object. Of course, we know how the rationales one has to complete, and on certain way which gives no information. But they proved that you can consider as a limit object the measurable functions in the 0-1 square. Yeah. Mm-hmm. And on that way you get, for example, a semi-ready type theorem for measurable functions. That's the only thing what I am saying about the interaction between different fields. So the whole thing started around in 2004, or already some discussions in 2003. I am not so sure. And it is still far from the end.
Yeah, Vera, you mentioned that several girls from that high school became mathematicians, but nevertheless, as you grew in your career in Hungary, you were always surrounded virtually entirely with men. How did this men's society receive you and react to you?
This was never an issue in my life, I must say, from the very beginning, from the age of 14, when I started to be interested in mathematics, that now it could be a disadvantage for me to be a mathematician because I am a girl.
So nobody ever suggested to you, even from your youngest year, that's not a girl-like thing to solve mathematical problems?
It was never an issue in my life in Hungary. It was never an issue in my own life at any other part of the world. But I must say that I had to learn that this is a serious problem when I came to the States, and maybe the first time in the middle of 60s, and then since that very regularly. And of course, the 60s were the most important years from the point of view of feminism. And then I had to learn that this is an issue. It is a very delicate issue, and there are very different answers in the mathematical world in Hungary. This was never an issue, or at least maybe I did not have sense for it, but I never felt any sort of discrimination. But you are among the men in Hungary, so you maybe know better than I do. Did you discuss that question behind me?
Okay, I can say what my impression was. I mean, as I grew up, I attended a mathematically specialized high school class. There were 39 of us, and 1/3 of that were girls, 2/3 were boys. And I didn't have the impression that there was any distinction either from the teachers or from the students themselves. We were very competitive, and whoever was the better problem solver was the better. That was really the interest. And some of the girls were very good problem solvers also. But I am always a little bit afraid that I am only representing really what my male point of view was. So I cannot say that that was how the girls in the class felt.
I think that any sort of quota or that sort of positive discrimination will not help.
One of the areas for which Hungarian mathematics has been best known over the past half century has been combinatorics. How did the Hungarian combinatorics school come about?
There are two different periods, actually, when combinatorics became popular, or not popular, but at least known. The first one is when Erdős and Gallai were students at the Eötvös University, and at that time Dénes König gave lectures at the Technical University, and they both went to attend the lectures of König. Now, it is important to mention his name also because König's book was the very first, as far as I know, book on graph theory. But at that time, the graph theory, what was presented there was matching theory and that sort of things, electrical networks, and this was in the 30s, and I feel for more than 30 years there was nothing. And now, how in the program for mathematicians included as an obligatory lecture graph theory.
Now you are in the 60s. No?
Now I am in the 60s. That before 62, I think, there was no program just for mathematicians. It was always a program for mathematics and physics, which included mathematics and physics, and officially it was a program for teachers. At that time, graph theory was completely different. We had a lot of almost isolated theorems, and this is what I really did in the very first year. And I think you never had a graph theory in the first year, did you? No. And the reason was that graph theory was not accepted as a subject what one should learn, what is important enough, and so there was a permanent discussion at the university that graph theory and number theory should belong to the curriculum or not. And therefore, it was an in and out. In some years it belonged, in some years not. But even at that time, when it was not necessary to take that course, there was always some sort of special course. So this means that in Hungary, I feel that young people had very early, in the early 60s, the possibility, or even more, was forced to learn some graph theory. At that time, easier to find problems, questions, unsolved problems on which young people can work and can have their own results. And this is what happened.
Who were the major mathematicians who somehow brought this subject?
Erdős was, but he was most of the time abroad, so there was no possibility to ask him to give a lecture. And the second was Gallai, who was already working on graph theory, and his results were best known.
Did Rényi have some role in this developing love in Hungary for combinatorics?
Partly Rényi, but for Rényi, probability theory was his main subject, and he had a chair there, so the whole probability theory was his responsibility. But Hungary was, I think, the first one where combinatorics, graph theory, discrete mathematics became a required course.
Required course at Eötvös University
for undergraduates. Yes, for undergraduates.
You were somehow the center of the community on every level. You were my first mentor, and so many other people's. You simply knew not only about their mathematical progress, but also their family and their lives and what is happening. And basically, all these people became, I should say, your friends. I think that I can say maybe that we have been friends for 4 decades.
Thank you what you are saying, but I think this is what everybody in the position I was did or even now should do.
I should mention the name of one of our colleagues. He was just 1 year my senior, who became then a close collaborator with you, Gyuri Elekes, who very sadly died at a young age of cancer. But the reason I'd like to mention it because Penrose tilings became a very important subject to you, and Gyuri Elekes produced a highly unusual birthday present for you that connects to this. Could you say something about that?
Yes, I mentioned already one birthday present, and this is the second one. He made with his own hands, actually, a so-called Penrose coffee table, which means that he produced an algorithm and he constructed this table, yes. But our connection was even stronger. So the last lectures what I gave at the university, I stopped to give maybe 6 years ago. It was a joint course we gave with Elekes on random structures. So we really had a very different-sided connection. So he was not just a student, I must say.